what I was saying, that using this velocity profile you can derive the shear stress profile, like the shear stress and the wall shear stress, the expression for the wall shear stress, and also the expression for the flow rate. Okay, that what is the flow rate through the pipe, that will depends on this pressure gradient. Okay, the viscosity of the fluid, the radius of the pipe, and all these things. I will not go into that details, because these are just uh, very simple. Okay, you can do it for yourself. So the concept which is very important here is that this analysis is valid for the fully developed flow only. Okay, and you have a parabolic velocity profile, but the velocity at the central line is the velocity at the central line is the maximum. Okay, and then it decreases towards both the wall, and at the wall the velocity is zero because of the no slip boundary condition. Okay, fine. So let us now do a similar problem where again we can solve the Navier-Stokes equation analytically. These problems is something which is known as Taylor-Couette flow, or so I discussed about Hagen-Poiseuille flow. Now let me just derive the velocity profile for for Taylor-Couette flow, or steady flow between concentric rotating cylinder. Okay, so I'll write it as steady flow between concentric rotating cylinder. Or this is also known as Taylor-Couette flow. I think he talked about this in the course. Yeah. So professor also discussed about the Taylor-Couette flow in class. So let me write it down. So the problem is something like this, that you have two rotating cylinders. I'll just draw the top view of the entire problem. So I have a rotating cylinder something like this as the inner cylinder, and I have a outer cylinder. Okay, and I wanted to calculate, and I want to calculate what is the so this cylinder is rotating at some speed, this cylinder is also rotating at some speed. Let's say these speeds are omega 1 and omega 2. Okay, and like in the inner gap between these two cylinders, I have a viscous fluid for what I wanted, like for which I wanted to know how the velocity profile looks like for uh, flow between two concentric concentric rotating cylinder. Okay, and let's, okay, so what I need to apply here, I need to apply the Navier-Stokes equation along again r, theta and z direction. The similar assumptions are valid for this problem also. The assumptions are quite similar for this problem as well. Okay, the assumptions are quite similar for this problem as well. So I have, this is omega 1 and I have these as omega 2. Okay, so I will not write the Navier-Stokes equation like in that form, but rather what will I do, from the continuity equation, what you know, in this case from the continuity equation, what you can say, it is again a parallel flow. That means only the v theta component of the velocity is non-zero, the Vr and Vz are 0. That means you have only velocity in the theta direction. You have the velocity only in the theta direction, not in the r direction and not in the z direction. You have the velocity only in the theta direction. Fine. So again from the continuity equation and from the assumptions of parallel flow, that means the flow is parallel around the axis of the two cylinders. Flow is a rotating flow around the axis of the two cylinders. There is no component of the velocity along z direction or along theta direction. Okay, so from the continuity equation you can say that v theta is a function of r only. Okay, v theta, velocity along the theta direction, v theta is a function of r. Okay, this you can say from the continuity equation. This is very important. Okay, now from the momentum equation in r direction, and there is no flow along z direction, so I don't need to write the momentum equation along the z direction. Okay, so momentum equation in r direction, I will not write the equation explicitly, but rather what I want to write is that what the velocity, what the expression you will get out of here. So you will get that dp dr is equal to rho v theta square by r. Okay, you will get from the r momentum equation. This expression you will get from the r momentum equation. Okay, these expressions you will get from the r momentum equation. What about the theta momentum equation? Momentum equation in theta direction. Like what you will get out of here from the momentum equation along the theta direction. From there, so only v theta is a function of z, right? So what I will get from here is that mu into dou r of 1 by r dou r r v theta is equal to 0. So if you solve this, what you will get is that v theta is equals to c1 r by 2 plus c2 by r. This will be the expression for your v theta. Now what are the boundary conditions in this problem? So the boundary conditions is that v theta is equals to omega 1 r1 at r is equals to capital R1. Capital R1 is the radius of sphere 1, sorry, cylinder 1, and capital R2 is the radius of cylinder 2. Okay, so what is the other boundary condition? V theta is equal to omega 2, sorry, I am writing it wrong actually. This will be capital R1, and also this will be capital R2 at R equal to capital R2. Fine. And if you put these two and you put these two boundary condition into the governing equation, what you will get is that, so what I want to write here is that instead of c by 2r, I'll put the 2 in the constant itself, so I'll write c1 into r plus c2 by r, as simple as that. So I simplified it again, plus c2 by r, and I will calculate what is the values of c1 and c2 using the boundary condition. So if you put the boundary condition and calculate the value of c1, the c1 will be something like this. C1 will be equal to omega 2 square, sorry, omega 2 r2 square minus omega 1 r1 square divided by r2 square minus r1 square, and b, that is the c2. So this is the expressions of c1, and c2 will be omega 2 minus omega 1 into r1 square r2 square divided by r2 square minus r1 square. Am I right? So these are the expressions of c1 and c2. If you put these expressions of if you put these two expressions of c1 and c2 and you write it down, the v theta expression, so v theta as a function of r will be equal to 1 by r2 square minus r1 square into what I am getting from here is that omega 2 r2 square minus omega 1 r1 square into r minus omega 2 minus omega 1 into, so I wrote it wrong, this will be small r and omega 2 r2 square minus omega 1 r1 square into small r minus omega 2 minus omega 1 into r1 square r2 square divided by small r. So this is the expression for velocity profile along the theta direction. Okay, and using this velocity profile you can calculate what will be the pressure, the gradient of pressure along the r direction, and you can in fact write the p as a function of pressure as a function of r. You can write that how pressure will varies along r direction. So how the velocity profile will look like here, if you draw the velocity profile in any section, how it will look like, it will look like this. So it will be like the velocity like this, velocity like this, velocity like this, velocity like this. So these will be your velocity profile. Okay, so these two derivations are very simple, you can go through it, and professor have discussed in details about the stellar Couette flow in class with the experiment, with the experimental with the video from experiments also, where you can see that for the different Taylor number how the flow become transient and then turbulent. That is discussed in details in class, I will not go into the details. So yeah, so I guess this is enough for today's thing. We will again meet in the next week.